When we observe the outer rims of spiral galaxies, they rotate far too fast to be held together by visible matter alone. The consensus conclusion is that this fast rotation is proof of a massive, hidden gravitational structure extending far beyond the baryonic disk. The standard cold dark matter model explains this structure as a collisionless, hierarchical cloud of particulate dark matter. But dynamic vacuum field theory, or DVFT, suggests these wells aren't made of particles at all. Instead, they are primordial defects formed during tachyonic rolldown, a rapid phase transition where the vacuum of the early universe settled into its current state. This diagram shows a mathematical degeneracy. On the left, the particulate density profile natively resolves to a constant circular velocity. On the right, the DVFT logarithmic potential resolves to the exact same flat velocity profile. Because both models marginally predict flat rotation curves, this observation cannot break the tie between them. To determine if the halo is a particulate cloud or a topological field, astrophysics must discard rotation curves and test stricter thermodynamic and morphological diagnostics. The bullet cluster collision is traditionally heralded as the ultimate visual proof of collisionless dark matter separating from interacting baryonic gas. Here we see a distinct 100 to 200 kiloparsec separation between interacting gas and lensing mass centers. DVFT replicates this offset because vacuum defects are potential wells without particles. Like a ripple passing through silt, the blue lensing mass glides through unaffected, leaving gas behind. We can evaluate both models using 3 rigorous benchmarks: thermodynamics, angular momentum acquisition, and morphological variance. The true physical nature of a halo is revealed by how it reacts to baryonic loading over time. This proves whether the halo has intrinsic thermodynamic memory or if it is merely a passive gravitational reservoir. In the standard model, infalling baryons must shock heat to the virial temperature and then cool radiatively on a timescale shorter than the dynamical collapse time. In the DVFT approach, baryons fall into a pre-existing vacuum scaffold. They dissipate energy while the defect undergoes a slow, intrinsic vacuum strain relaxation. This diagram illustrates the DVFT vacuum relaxation equation, showing how the structure naturally supplies configurational entropy to balance baryonic cooling. Applied to extreme systems like dwarf galaxy DDO-154, both models predict its dark-dominated virial temperature of 91,000 Kelvin. However, DVFT achieves this thermal state purely through vacuum relaxation. It requires zero explicit kinetic virialization or shock heating of a secondary dark particle component. Observed galactic halos exhibit complex disequilibrium and cooling efficiencies that align natively with an intrinsically thermodynamic vacuum structure. Standard cosmology faces a historical angular momentum problem. Simulated galaxies consistently lose too much angular momentum during hierarchical mergers, destroying extended spiral disks. The standard mechanism for generating spin is tidal torque theory, which relies entirely on the gravitational tug of neighboring structures. To match observed disk sizes, researchers rely on massive statistical tuning, precise feedback prescriptions, and highly specific spin parameters. This 3D vector map visualizes the DVFT topological alternative. Here, angular momentum is inherited directly from the primordial phase winding of the vacuum field. The topological equation shows the total spin parameter decomposes into tidal forces and intrinsic topology, driven by the defect's winding number. This native geometric momentum perfectly supplies the high angular momentum needed for exponential disks, completely bypassing the catastrophe seen in particulate simulations. Galactic rotation is a native geometric property of the vacuum, rather than a tidal accident requiring algorithmic correction. We can test morphological predictions by comparing NGC 2403, a high surface brightness spiral, to UGC 128, a low surface brightness spiral. This chart highlights a data anomaly. Both galaxies share an identical flat rotation velocity of 130 kilometers per second, but UGC 128's disk radius is 4.5 times larger. Standard cosmology requires extreme concentration variations and customized feedback to force this difference. DVFT requires zero post-hoc tuning to solve this. The ratio emerges automatically from the differing primordial defect winding numbers, or shape tensor axis ratios. Wide variances in galaxy morphology are fossilized memories of primordial vacuum geometry. While standard paracle models can technically reproduce the data, they require a highly indirect, parameter-heavy framework to do so. This matrix maps out the tuning requirements needed to align standard particle halos with observable reality. The standard model relies on specific concentration metrics, disk instability thresholds, and tuned merger rates to match what we observe. Conversely, every observable in the right column natively derives from that single mechanism we discussed, tachyonic roll-down followed by Kibble-Zurek freeze-out. Occam's razor heavily favors the model that provides the gravitational well, entropy source, and angular momentum natively from a single field structure. A physical theory earns its keep by making falsifiable predictions about future observations. The standard model predicts hierarchical halo assembly. DVFT predicts vacuum relaxation-driven halo widening. This graph plots halo radius against cosmic time. At a fixed baryonic mass, DVFT dictates that high redshift halos will be measurably tighter than low redshift halos as the defect slowly relaxes. Upcoming high-resolution surveys like Euclid, Roman, and the Square Kilometre Array are positioned to directly measure this redshift evolution and test the dark matter degeneracy. The evidence points to a reality where the dark sector behaves completely unlike matter. The dark halo is an evolving geometric medium encoded with the topological memory of the